Okay, Bismillahirrahmanirrahim. So let's start this lecture. So today we will start the topic that is the forced vibrations. In fact, it is damped forced vibrations. Now, previously we are studying about free vibrations. This is what we have studied previously in this course. And in the free vibration, you know that if you plot the response of the system, let's say you have a mass spring system and you have a damper also present. This is your mass with the stiffness K and the C. What happens that your amplitude decays over time. As told you, you can take this decay as the logarithmic decay. Clear? So this is the free vibrations. The frequency of this free vibrations, the frequency of this free vibration is generally called, as you know, natural frequency. Natural frequency. So this is what we have done before that. Now we are interested in this topic. We are now interested in the forced vibrations. And what is a forced vibration? If any force is applied on a system that is from any external source, the vibration that a system exhibits is called forced vibrations. There are many examples of forced vibrations, but before going to the examples, two things are very necessary. The force which is coming from external source, it must be periodic, which means it must be repeated or sinusoidal, and it must be continuous. There are two conditions of this force. The force that comes from any external source, it must be periodic and it must be continuous. Common examples of forced vibrations is an earthquake. Earthquake is a very common example in which your structure of building vibrates because of the shaking of the earth, and the shaking of earth is because of the forces generated by the earth to develop earthquake, and that is generally called as forced vibration. Similarly, the vibration of aircraft wing is also forced vibrations. Here the force came from the air, because the wing interact with the air and the air produces force on the wing that causes the wing to vibrate. The third application, general application, is there are so many, like in machines. Is machines very common. These vibrations are very common. This may be due to unbalance. The unbalance also causes forced vibration. It may be misalignment of the shafts, and it can be any other source. There are so many sources of vibration machine. So these all are the forced vibrations. Now the modeling of forced vibration is slightly different from free vibrations. Why? Because in free vibration we do not consider any external force, but in this case you have to consider the external force, and that is why the idea of the understanding the modeling of the forced vibration is very important in analyzing the system. Now before going into the modeling of the system, I just show you a video. Just look at this video. So this is basically collapsing of the Tacoma narrow bridge. This is the Tacoma narrow bridge. It collapsed soon after its construction. In fact, it was constructed in 1940 during the Second World War in USA, and soon after construction, about 2 months later, it starts to vibrate like this. You can see these vibrations. You can see these vibrations. They're very violent vibrations. Now, after about 6 months of its construction, it actually collapsed. That is a very, you can say, a very alarming situation for the designers. Why? Because it has never happened before, but because there is a very peculiar behavior of this bridge under, and what is a gust? And gust generally is the strong air, strong wind with a velocity ranging from 40 to 60 kilometers per hour. This is what the gust is. So in this gust, this bridges vibrates, and ultimately after about even within 6 months, at that time in 1940, it cost millions of dollars, and soon after construction actually collapsed. If you look at the collapse of this bridge, actually collapsed, and you can see that right now that this bridge actually collapsed. Now, when this bridge collapsed, the very major questions has been risen up, and that is why, what is the major cause of failure? It was the 10 years later that they finally realized that this failure is because of the flutter, which at that time is not known to science, and that is, and flutter is nothing but a self-excited forced vibrations. Flutter is a very peculiar type of forced vibration, generally happens in aircraft wings or bridges or the structure that is prone to the wind. But in any case, this is also the forced vibrations. Now, in order to save a structure from disaster, we actually are very, you can say, careful in designing the system so that if any force come from a system, it should not vibrate in such a way that a system should collapse completely. Now, one idea that you should have clear in your mind, you cannot eliminate the vibrations. This is for sure. You cannot eliminate the vibration in any system. What you can do only is try to minimize those vibrations so that the disaster should not take place. And I'm again repeating, what you can do is, you cannot eliminate vibrations from any system, because you can only eliminate vibration, eliminate the force, which is not possible in most of the cases. That's why what you can do by properly designing a system such that you actually reduces the chances of failure, or you can increase the life of a structure by keeping the vibrations at a very low level, so that your structure will have a longer life. And you can do that by properly designing the your system. So we start modeling the system. I hope you understood the concept, or you imaginated the idea that how force vibrations takes place. Now, if we just draw using, we start doing modeling of the system by developing a very basic model, which we have done before. So we have C, constant C, we have this constant K, and this is M. C is the damping constant or damping coefficient, K is the spring constant or spring coefficient, and M is the mass. So there is a motion x of t here. Now, in the forced vibration, you consider that there is a sinusoidal force or the continuous force, periodic force, that exists on this mass. There is a continuous force, which is F of t, that actually exerted on this mass. Now we want to model this system. So for this we have to use the same principle, that is summation F is equals to mx double dot, which is the Newton's second law of motion. Now mx double dot remains the same, which is mx double dot right hand side. On the left hand side, the forces which are actually the forces were actually present within the system, or the restoring forces, you have to write it with the minus sign. Clear? So if this mass moves in the right direction, you have the spring force in the left direction equals to kx. You have also a damping force in the left direction equals to cx dot. Clear? So we have minus kx minus cx dot. Clear? These are two restoring forces, but this force comes from the external source. So what you have to add up. Okay, you have to add up f of t. Why we have written with the plus sign? Because this is the external force. Clear? If the force is internal and restoring, it will be written with the plus minus sign, as you can see in both these forces. But because f of t is an external force, it came from the source which is from outside the system, then you have to write it with the plus sign. I hope it will be clear to you. The f of t is written with the plus sign. Now in Newton's second law of motion says you can't write anything on this side. This is not possible. Newton says you don't. What have to write is only on the left side, and every summation of force should be on the left side. If it is within the system, it should be written with a minus sign. If it is exists outside the system, it is written with the plus sign. If I rearrange it, you get mx double dot plus cx dot plus kx equals to f of t. Okay, the right hand side is not equal to 0, and such type of equations are called second order non-homogeneous linear ordinary differential equation. This is what it is called. Clear? It's called second order non-homogeneous linear ordinary differential equation. Why it is called second order? Because the derivative is second derivative. And why it's called non-homogeneous? Because the right hand side is not equal to 0, but rather is equals to f of t. And what is linear? Because the power of x is 1. X double dot x or x dot is 1. Now the equation which is second order, okay, before that we consider that f of t is something like some f naught sine times cos omega t. Where if you draw this force function, where this is the time axis and this is the f of t axis, your response looks like this. Your response looks like this, where this amplitude is nothing but f naught, and the frequency, so this is the time, which is equals to 2 pi by. Okay, so this is the force. Now it can be more complicated for many different applications. The f of t can be complicated. In my own PhD thesis, this f of t roughly takes about 7 or 8 lines. It could be complicated or it could be simple as well, depending upon your application. Clear? Now, why cos omega t? Why not sin omega t? You can also write the sin omega t. Both are the periodic functions. But for a certain sake, I written as cos omega t. But if even you write sin omega t, it's fine. Okay, for this equation, if I divide it by m, so what you get is c over m x dot plus k over m is equals to f naught by m cos omega t. So what I'm letting is, let capital F naught divided by m, which is force, peak force per unit mass, as small f naught. Just for the sake that the derivation becomes relatively simpler. So, and c over m is written as, from your previous understanding, is written as 2 zeta omega n x dot, as we have done in free vibrations, plus k over m is nothing but omega n square x equals to f naught cos omega t. This is your governing equation. This is your governing equation of the system. Now the next step is try to solve this equation. So we are interested in finding the solution of this forced vibration systems. Okay, for that, so just write again x double dot plus 2 zeta omega n x dot plus omega n square x equals to f naught cos omega t. Now for the non-homogeneous system we have two solutions. One is generally called as complementary solution or homogeneous solution, and second is called as particular solution or non-homogeneous solution. Now for a complementary solution, if you remember the solution of ODEs, you will remember that for a complementary solution you have to put right hand side for x of c, put right hand side of the equation, above equation, equal to 0, this equation. And you know what you get is a free vibration response, as we have done previously. So it indicates that we actually know what xc of t is, which is the solution of free vibrations, and we have done it. It is minus zeta omega nt c1 sine of omega dt plus c2 cos of omega t. We have done before. This is the solution of free vibration. Now we are only interested in the solution of forced vibration. That is only difference in this equation. So we are interested in xp of t. Clear? Now for that, for a solution of xp of t, I am using a very specific approach to solve, that is called the complex number approach. Complex number approach. There are other approaches as well, like variation of parameters, like method of determining coefficients, and maybe the other method, but I think this method is relatively simpler to understand, so I have used this method to solve the equation. As we have told you, we are only interested in xp of t, and because we know xc of t previously, so just you have to add two solutions to get the final solution of the forced vibration systems. For xp of t, we consider small f naught cos omega t, which is the equation, which is the formulation on the right hand side. Okay, before that, just give you an idea before writing it. You know that e iota theta is equals to cos theta plus iota sin theta. Clear? This is what you know from your previous understanding. Of theta is omega t, so iota omega t is nothing but cos omega t plus iota sin omega t. This was you previously. Now the f naught cos omega t can be written as f naught into the real function of e iota omega t. If you see that the cos omega t is the real part or the real function, real part of e iota omega t. So what we can say now, f naught into cos omega t can be written as f naught into the real part of e iota omega t. Clear? Now what you can, okay, this is the constant number, so if you take it within the bracket it works fine. So f naught cos omega t so if you take this f naught within the brackets, it become real part of f naught e iota omega t. This is what right hand side looks equal to. So it's a real part of some f naught, which is a constant number, times e iota omega t. Similar is the case for the, if you take the so what I'm interested in xp of t. So if I want to express xp of t in the same way as I've expressed f naught cos omega t, so it's some real part of some x bar e iota omega t. Now what x bar is, I don't know, but because as I know that the f naught cos omega t looks like in a similar way as this, and from the comparison of the previous this function, we know that x bar is some constant, it's some combination of constant that we have to determine to find the solution of the system. So now if you want to write the equation again, because we are only interested in the particular solution, so instead of writing x double dot only, we write x double dot p plus 2 zeta omega n x dot of p plus omega n square x of p is equals to f naught cos omega t. Why written xp? Because we are interested in the particular solution. Now for putting this function in this equation, what we have to do, first take the derivative. So x dot p of t is nothing but real part of some x bar iota omega e iota omega t. And what is x double dot p of t? It's nothing but, if you take the derivative again, so it will become minus omega square x bar e iota omega t. And someone is pondering why minus comes from. It comes from iota into iota, which is iota square, and is equals to minus 1. That's why written with the minus sign. If you put both these x dot p and x double dot of p in this equation, what you get is the real part of minus omega square x bar e iota omega t plus 2 zeta omega n into real part of x bar iota omega e iota omega t plus omega n square real part of x bar e iota omega t is equals to real part of f naught e iota omega t. So if you look at this equation, the right and left hand side looks similar. That's why we have taken the converted the equation into the complex number. Okay, so as you can see, the x bar e iota omega t, this is common in all terms. So what we can do is to take this common and put the real function outside the brackets. So real part of minus omega square from here plus 2 zeta omega n from here, iota omega from here, plus omega n square, this is within the brackets, times x bar e iota omega t is equals to, is equals to the real part of some f naught e iota omega t. Clear? Now if you apply the real function on this equation, so real function can only apply to iota omega t, which becomes cos omega t, and also it becomes cos omega t, which is cancelled out. So you end up with x bar, if you take this in the denominator on the right hand side, x bar is nothing but f naught over minus omega square plus 2 zeta omega n iota omega plus omega. This is what the x bar, this is what the value of x bar we are actually interested in. That's why I've taken all this procedure, adopted all this procedure to actually find out what is x bar, so that if we put x bar in this equation, we actually get the solution of xp of t. Now rewriting again, x bar is nothing but f naught over, if I take the real and imaginary part separately, so omega n square and omega square, they are both real parts, and 2 zeta omega and iota omega is the imaginary part. So just put this value here. So omega n square minus omega square, this is the real part, plus iota 2 zeta omega omega n, this is the imaginary part. So in fact we have two, now the complex number in denominator, which is omega n square minus omega square, which is the real part, plus 2 zeta omega n omega, which is the imaginary part. Okay, so if we let v is equals to omega n square minus omega square and w is equals to 2 zeta omega omega n, and take u is equals to v plus iota w, then x bar is nothing but f naught over u. Okay, to take this iota from denominator into numerator, you have to rationalize by its conjugate. Okay, so I have multiplied and divided by its conjugate, u conjugate, which is nothing but u minus iota w, as you know from previous understanding of complex numbers. So if you solve this, this will become f naught u bar over u into u mod, so this become v square plus w square. And if someone is confused in this, so we just solve it. So v plus iota w into v minus iota w. If you multiply both, what you get is v square minus iota w square. Clear? And that is nothing but v square plus iota, sorry, not plus, minus iota square w square, iota square is minus 1, we get equals to v square plus w square. This is just for the sake of your understanding. Clear? Now in fact now the complex number is moved into the numerator. So what you can now see, now after that we just plot a u and u bar on a complex plane. So we have a real plane here, imaginary plane here, and if I just draw the v, so v is on the real part, so this is v, and w is the first, the u is actually so this is your w and this is your minus w. And if I draw the resultant, so this is the resultant, and the resultant is nothing but u mod, and the resultant of this is nothing but u bar mod. Okay, I hope you understood. And the angle is theta. Now this angle, if you just write here, theta is equals to tan inverse fw over v, and that is equals to 2 zeta omega omega n divided by omega n square minus omega square. And just simplify the taking omega n square common from denominator and dividing it above, you get 2 zeta, sorry, you get tan inverse of 2 zeta omega over omega n divided by 1 over omega square over omega n square. Clear? So this is generally, this theta is called phase angle or phase difference, which we will discuss later. But this angle is theta is very important, in determining the response of the system. Okay, the idea of doing all this is try to express u bar in terms of u. So what I mean is u bar is v minus iota w, you know from your previous understanding. Okay, so if you want to express v in terms of u bar, so it is nothing but, if you from this graph you can see v is equals to u bar, u mod cos theta, and w is equals to u mod sin theta. If you look at this, again this v is represented as u mod cos theta and w is represented u mod sin theta, and using the basic trigonometry you can actually write it. Okay, so if you write in this equation, so v is u bar is nothing but u mod cos theta minus iota u mod sin theta. Clear? You also know that from this graph u mod is equals to u bar mod. The magnitude of both are same, and if you don't if you confuse on this step, just do it yourself, you will realize that they are both equal. If you take u bar common and replace it by u bar mod, become cos theta minus iota sin theta. So the equation become u bar is equals to u bar mod cos theta minus iota sin theta. Instead of writing like this, if I express this into, look at this, cos minus theta plus iota sin minus theta, and I can express like this. Why? Because minus actually dissolve in cos theta, but it comes out on the left side from sin theta. So you can then say that u bar is nothing u bar mod e minus iota theta by using the Euler's formula. So that is what we are interested in. This is that's why we have drawn a graph, and that's why we want to convert this into this system. Now you have to put the value of u mod in this equation. So what you get is x bar is nothing but f naught, and what is u mod? U bar mod e minus iota theta divided by v square plus w square. Now you know that since u bar mod is v square plus w square square root, and this is again from this graph. So if you put this value right here, so you see it's a square root, so one square root will cancel with the below, you end up with the square root in the denominator. So f naught e minus iota theta divided by square root of v square plus w square. Okay, this is what x bar is equals to. Now if you put this value of x bar in this equation, it's of xp of t, which is the solution where we assumed. So xp of t is equals to real part. What is x bar? Is f naught e minus iota theta divided by square root of v square plus w square into e iota omega t. Okay, we know from your basic understanding of mathematics, if bases are same, the power can be added. So both e powers can be added. So you end up with xp of t is some real part of f naught iota omega t minus theta divided by square root of v square plus w square. Clear? So just taken iota common from both terms, taking omega t as the first term and theta as the minus term, because theta has with the minus sign, so you can write like this. Now if you apply the real function on this within the brackets, now the very interesting thing comes, this become cos, or whatever the theta is, you can write like that. So xp of t is nothing but small f naught, and e iota omega t minus theta is cos omega t minus theta, which is the real part. So cos omega t minus theta divided by square root of v square plus w square, and in fact which is equals to, if you put the value of f naught and v and w, so small f naught is capital F naught divided by m cos omega t minus theta divided by square root, and this v, if you, it's omega n square minus omega square theta omega n whole square. This is our xp of t, the particular solution. Slightly simplifying it, if I take omega n4, if you take omega n4 out of the brackets, become omega n square. So we have to divide omega n square with this term and term also. So when you divide it, what you end up with, f naught over m cos omega t minus theta divided by omega n square, which is in the outside of the square root. This will become 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. This is what we left in the denominator. Now k over m, omega n square is nothing but k over m, so m is cancelled with this m, so you end up with the final form of the particular solution as f naught, and k will become in the denominator of f naught cos omega t minus theta divided by square root of 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Clear? This is our final solution of the particular solution. Now the total solution, if you remember, as in the first slide, we have written it's xc of t plus xp of t. So we need to know the complementary solution. So x of t is, what the complementary solution is, e minus zeta omega nt c1 sine of omega dt plus c2 cos of omega dt plus, what is the particular solution, f naught over k cos omega t minus theta divided by 1 minus omega square omega n square whole square plus 2 zeta omega by omega n whole square. This is the final solution of a forced vibration system. So we have the complementary solution. So this whole is xc of t and this whole is xp of t. So this is the two solutions. Clear? Now just for sake of how this solution will behave, so I just show you a picture. Just hold on. Okay, if you look at this response, this is basically sometimes called H, this is called homogeneous solution, or it's also called xc of t. So if you look at this, as you know from your previous understanding of free vibration, that the homogeneous solution actually dies out after some time. Time here is written as tau. This is the time where the solution dies out. And if you purely draw the particular solution, it looks like this. Now the amplitude does not decay in forced vibration. It keeps the same as long as the force is present in the system. If you look at the equation, if you put F naught equal to 0, the whole solution dies. It's finished. It means that as long as F naught remains in the system, then definitely you have the solution remains, otherwise it will die out. But when both solutions are added together, so we have a transient behavior till tau. If you look at this, this is called transient behavior, and after tau only xp of t remains, xp of t dies out. Clear? So this is how solution behave. So if you look at the case in tau, so you see the resultant vibrations are not with a single rather it's actually a very transient kind of response. Okay? Like drawn with the red line. Now why we actually, okay, after some tau is generally in many real applications is the order of milliseconds or maybe fraction of a second. So it dies out, the homogeneous solution or the complementary solution dies out very quickly, and what actually remains is the particular solution. Now someone can have a very if you have a question in your mind that why we then consider the complementary solution. Now in some phenomena the transient behavior or some phenomena are the you can say a millisecond phenomena. For example, if you find a missile from a base, so vibration that induced into a missile as well as onto the base is a millisecond phenomena. Clear? So in this particular scenario, you have to consider the transient behavior or the complementary solution along with the particular solution. Similarly, if you fire atomic bomb again is a millisecond phenomena. So that in this case you actually want to capture both solutions. But in many applications, like in vibration of an aircraft or an earthquake, we are mostly interested in the particular solution. So again, it depends on the application on which you are applying this solution. So it could be you have to, in some cases you have to consider complementary solution, in some cases you don't have to consider the complementary solution. In both the cases it works fine. So I hope you understood this concept, slightly modifying the particular solution. So if I take capital XP, so capital XP means that I have to put cos omega t minus theta is equals to 1. So this is what I have to consider to get the maximum amplitude of vibration divided by square root of 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. So we have to put this equals to, so omega cos actually vanishes. Clear? If I take this in the denominator of the left hand side, so this will become just right here, this will become 1 over, and this is f naught over k. Now this left hand side is called transfer function. And what is the transfer function? It's nothing but the ratio of output over input. So if you see xp of t, this is your output because it's an amplitude of vibration because of input, which is what? Force. So this is your input. And this factor is called as amplification or magnification factor. That factor will decide that how your system will respond in a particular way. Now to visualize this behavior, just look at this response. Just look at this response. Now here this term is what is written here. We just taken k in the and xp rather than x, it's fine. Now on the right, on the y-axis, that is xk over, which is the transfer function, and on the x-axis we have the frequency ratio, which is this as well as this. So it's written here. So when you draw it for different values of zeta, and if you know for free vibration, the system can be underdamped, critically damped, and overdamped. This is still the case for forced vibration. In forced vibration, system can be underdamped, system can be critically damped, system can be overdamped. So just look at this. So what happens is, and look at mathematically, if the omega over omega n is 0, now remember what is omega and omega n. Omega n is the natural frequency of the structure, which is under root k by m, and omega is the forcing frequency. Forcing frequency means frequency of the force that is applied on this system. Frequency of the force, it can be earthquake, it can be air, it can be, in the case of machines, faults, it can be anything. The frequency of that particular force is the omega. So omega, if omega over omega n is 0, if you put this value in this equation, so this term goes to 1, and zeta is 0, this term goes to 0, so you get 1 out. You can see this starts from 1. At omega n equals 0, it starts from 1. Interesting thing is, when omega over omega n equals to 1, now this is generally called as resonance. In resonance, the forcing frequency becomes equals to natural frequency. And what happens, if you look at this diagram, what happens at zeta equal to 0, the amplitude actually becomes infinite. Look at this peak reason, it goes to infinite, which indicates, and if you can also verify it mathematically, if you look at this mathematically, just see, if I put omega over omega equal to 1, this term goes to 0. If zeta is 0, this term also goes to 0. So 1 over 0 is infinity. So your transfer function actually goes to infinity, which means your amplitude of vibration actually goes to infinity, and the structure will break. Now at resonance, if you apply some damping, like you can see here, if you apply some damping to a system, you can control the amplitude of vibration. You can control the amplitude of vibration at resonance by applying the damping. But if you look at this response, when omega over omega n is equal to 3, the amplitude is very small. If you look at this is order of 0.1. Now this indicates that even you have a very little resonance, or sorry, little damping or no damping, if you keep this omega over omega n greater than 3, you have very small amplitude of vibration. That's, I'm saying that this is how to control vibrations. So what you have to do, first you have tried to keep omega over omega n greater than 3, so that even with a very small damping of 0.05 or maybe 0.1, you actually get a very small amplitude. The second case is, in some cases you can't do that, and what happens, your amplitude become very close to your frequencies are very close to 1, and resonance occurs. So what you do then, you try to apply sufficient damping so that you can have a limited amplitude. That is how this factor, which is called amplification or magnification factor, works, and you exactly know which parameter to change so that you can control the vibration. This is what I am talking you about in the start of the lecture, that we model forced vibration to try to understand which parameters are important in order to control those amplitude of vibrations. Clear? Otherwise, if we do not control the frequency ratio, the amplitude becomes so high and structure will eventually break. That actually happens, as I told you in the Tacoma Narrow Bridge. It happens a lot, and the biggest reasons of the failures are resonance, in which the frequency become very close to the natural frequency. That was you have to avoid in many real applications. Now apart from that, you have to just see the phase response if you remember, is this formula, which is theta is equals to tan inverse of 2 zeta omega by omega n divided by 1 minus omega square over omega n square. So here it is theta, and here it's again the frequency ratio. So here frequency ratio is theta. Now this is, now I just draw a line here. Now this is pre-resonance, or the is pre-resonance, or here, and this is the post-resonance. Clear? So this is okay. One thing that you have seen here, that in the pre-resonance, mostly your angle is less than pi by 2. In pre-resonance, if you look at those lines, for this line, or this line of a different value of zeta, you get the angle equals to less than pi by 2. For that, if the right hand side is greater than pi by 2. So you can see that it is less than greater than pi by 2 depending upon the value of frequency ratio and the zeta. Similar is the case. Now if you put the, like, just justify with the formula that if omega over omega n equals to 1, so in the graph, but you can see the angle is exactly equals to pi by 2, and just see here, if omega n equals to pi by 2, the denominator actually goes to 0. Anything goes to 0 is actually infinity, which is pi by 2, as you know from the laws of trigonometry. Clear? And you can put every other value, omega n can be 0.2, 0.3, and then angle come out to be, you can use different value of zeta to get the angle. So main idea is, okay, what is actually theta? Theta is actually, so if this is your force response and this is your time response, system response, so the phase angle between your force and the displacement is theta. It can be less than 90 if you are operating in a pre-resonance. It can be greater than 90 if you are operating in the post-resonance. Again repeating, if you are operating in the pre-resonance, you have an angle less than 90, as you can see in this graph, and if you are operating in the post-resonance, the phase difference between force and the displacement is greater than 90. Now phase is one very important to understand. Let's say, for example, you have a value of 3, for example, just give you an idea. Now 3, the value of transfer function of 3 also exists in pre-resonance. This is pre-resonance, and also exists in the post-resonance. So both value come out to be 3. Let's say you have measured the value of 3. Now you don't know whether it's a pre-resonance or a post-resonance, because in both cases the value is 3. Now the phase will decide, the phase will tell you whether you are in the pre-resonance or in the post-resonance. I am again repeating, if you have an amplitude and you measure it, you are not sure whether this amplitude is in the pre-resonance state or in the post-resonance state. At that particular scenario, your actually phase will tell that whether you are in the pre-resonance or the post-resonance, because the pre-resonance the angle is less than pi by 2, for the post-resonance the angle will be greater than pi by 2, and you will see that in your lab experiments the phase will come out to be, you will see that on the software, that when you apply a force on your vibrating beam or the vibrating mass, you will see in the pre-resonance angle is less than 90, and in the post-resonance angle is greater than 90. I hope understood. We have completed the modeling of the basic forced vibration. Clear? Now in this lecture also, because in the coming week we have to solve some problems from the exercise as well as some example problems, so that's why I am completing the derivation in this lecture, so that you completely understood why we are doing this. Now for your case, for your course, we have taken one application of that is the rotational unbalance. taken only one application of forced vibration, that is rotation unbalance. There are, as I told you, there are maybe thousands of applications in which a forced vibration takes place, but you cannot solve all those applications. But for your course at the bachelor's level, we only considered the rotational balance. And what is the rotational balance? Rotational balance is you have a rotating disc, and what you want is your center of rotation is on your center of mass. This is what the condition is. You want that your all mass is centered around your center of rotation, so your body remain balanced. But if, let's say, you have a piece broken out from this disc, let's say, so you're actually, the center of mass moves slightly in the opposite direction. So what happens, that it creates a eccentricity, which is called as E. It creates an unbalance. This creates vibrations in your system, and this vibration in some cases can be very disastrous. In industry, cement industry, or in oil industry, the most common problem in the rotary machine is an unbalance. Most common problem. I recently attended a training at Pakistan Homogeneous Commission in the start of November. So we have done a lot of analysis on this, and the analyst he came for the training told me that 80% we have the problem that occurs in the industry is a rotation unbalance problem. So we have to look into the one application, which is a rotation unbalance application. Okay, so for the rotational balance, okay, so what we consider is, it's a slide. I'm not going to the complete modeling. So what we have is a machine. This is a machine. On this, there's a small mass which is rotating, and the small mass is an unbalanced mass. This is unbalanced mass, located at distance E from the center, and there's a spring and a damper applied in beneath. Now, due to this mass, we have a force. If you remember, we have written F of t, as some F naught cos omega t. In case of rotation unbalance, we have to write this force. Okay, instead of doing this, we just write like this. We just write like this. So total displacement. Okay, so we have a displacement of this. This is the total mass, which I am now highlighting. This is the total mass which is moving up and down by x. So the total displacement is x which is this, plus the E, and this is sine omega t. Now remember, this eccentricity, the amplitude is maximum when this mass reaches at the top point. Clear? So because when it is along the line of the force, which is this equilibrium position, the force is minimum, it is maximum and its peak point, and this is governed by sine. So total displacement is x, which is the motion of the mass, plus E sine omega t. Why? Because this E is rotating with a certain frequency, which is omega. Clear? So this is our system is, and the total non-rotating mass. Non-rotating mass is, there is a small mass which is rotating. So total non-rotating mass is capital M, which is the total mass, minus small m, which is the mass which is small mass which is rotating. This mass, which is rotating. If we subtract the capital M, which is the total mass, minus small m, which is this mass, so we end up with the total non-rotating mass is capital M minus small m. So there are two inertial forces. One is due to this displacement and second is due to this mass. So just to write the inertial equation, so summation F is equals to mx double dot. So in this mx double dot, so we have displacement, so we have total, so this is because of the small m, so we have there's inertial forces of two masses, one because of small m, one because of the capital M. So small m and d square by dt square into x plus e sine omega t. This inertial force is due to the rotating mass, and second inertial force is due to the non-rotating mass. You have to just understand it. The first inertial force is due to the rotating mass. That's why we multiplied it only with a small m, which is a rotating mass. The second inertial force is due to the non-rotating mass, which is capital, is equals to minus kx. So we have two springs and they are in parallel. So k by 2 is k minus cx dot. This is our governing equation. So okay, just solving it, you get m, this will become x double dot and plus m e. If you take the double derivative of e sine omega t, it become e omega square, so it will become minus. There are two steps you can solve it. Sine omega t plus mx double dot minus small mx double dot, multiply x double dot in the bracket, is equals to minus kx minus cx dot. So if I take this, will be cancelled with this. So if I take this term on the right hand side and these terms on the left hand side, so mx double dot plus cx dot plus kx equals to me omega square sine of omega t. Clear? So x double dot plus c over capital M x dot plus k over capital M, which is the capital M is the total mass. Clear? Capital M is the total mass. So which is k over mx equals to, and if you compare this with f naught cos omega t, as told you, whether write sine omega t, in this rotating mass, the sine omega t is a function, because I told you rotating mass, when it moves, it comes to its equilibrium position, the force is 0. When it comes to maximum position, the force is maximum. That is governed by sine. So this is your f naught. If you compare it with this equation, this is your f naught. So me omega square sine omega t divided by capital M. Clear? So the idea is simple. Just using the previous solution, which is xp of t, f naught over I just write the previous, slightly previous step, so you cannot get confused with that. Remember, before cancelling the omega n out, I have just written this, which is omega n, which is 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Now for the application of the rotation unbalance, you can see the f naught. So in this case, f naught is me omega square, and if you compare it, it's a centrifugal force that is applied because of the unbalanced mass. The small m is here, the capital M, which is the total mass of okay. So just write here so you can get confused. So capital F naught is me omega square. The small m here is the capital M, The natural frequency is k over capital M under root. Clear? If you put all those values in this equation that we have derived previously, so xp of t, so xp of t is nothing but me omega square divided by capital M. So instead of small m we write capital M. Cos यहाँ पे we write sine because it's a sine function, divided by, and omega n is k over capital M under root 1 minus omega square over omega n square whole square plus 2 zeta omega by, okay, we do not write this. So just write omega n square instead of k over m, omega by omega n whole square. Taking omega n above in the numerator, so just writing like this, me over m omega by omega n whole square. So this is the only difference in the equation. There it is written f naught over k. Here the only factor, the difference of the difference is this factor, nothing else. Clear? So again, if I put this equals to 1 for the maximum case, so the xp of t, so for maximum this small x become amplitude with capital M is equals to me over capital M into omega by omega n whole square divided by the same factor which I am not writing again and again. Okay, if I take this in the denominator on the left hand side, now this me generally called as unbalance, and you can see that if I put this E equal to 0, what is E? It's a distance from your center of rotation to the center of mass. If this goes to 0, which means your body is balanced, then what happens? Then you actually vibrations goes to 0. Okay, so if you look at this equation, so you can now see that if you remember the forced vibration, here it is f naught over k, but here it's me over m. Now if you look at this response of the rotational unbalance, and let's say compare it with the general response of the forced vibrations, just showing you both the responses just for comparison. You can now see that the only difference is in forced vibration, this is for rotation unbalance. For forced vibration start at 1, for the rotational unbalance it start at 0, and for the for high frequency ratio like 3, amplitude is very small, but here it's close to 1. So only otherwise the response is exactly the same at resonance. When omega equals to 1, the amplitude become very high, as you can see in both these graphs. And the starting and ending point are different because of the above factor. In this case it is 1, the numerator, and this case is omega by omega n. It's the frequency ratio. That's why the starting and ending point is different, but in between the starting and ending points the response is exactly the same. So what I am showing you about, this is a one application in which you apply the concept of forced vibration, and what we identified is what is the force equals to, and that is because of the unbalance is equals to me omega square. So you see, if you put E equal to 0, which means your center of mass becomes center of rotation, then your F goes to 0. So when F goes to 0, there will be no vibrations. Yeah. So the only way of reducing the unbalanced vibration is try to balance the body which is rotating so that your E goes to 0. This is what your main idea is. Clear? Now, just we are towards the end of this lecture. So this is our application. So going back to our previous total solution of the forced vibration, which is E minus zeta omega nt C1 sine of omega dt plus C2 cos of omega dt plus f naught over k cos of omega t minus theta divided by 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Okay, if this is the rotation unbalance, the xc will remain the same. Only xp of t, which is this, can be then written as me over capital M omega by omega n whole square sine of omega t minus theta divided by the same factor in between. This is for the rotation unbalance. Now you also remember that we have written the another solution for free vibration, that is xe minus zeta omega nt sine of omega dt plus phi. And as told you when we are modeling the free vibrations, that this solution is same as this solution. This is both the solution of the free vibrations. But for the particular solution, it can be, in case of generalized force, can be like this, but in case of rotation unbalance, you can replace the f naught over k solution with me over m solution. Now, just for a generalized case, we have used this solution here. So this is f naught over k cos of omega t minus theta divided by the same square root. And if you want to, because there are two unknowns, one is x, second is phi, for that you have two initial conditions. Let's say we consider, so x of 0 here is x naught and x dot of 0 is equals to v naught. And what I am expecting is, for this solution you can now put the initial condition to get the constants out, although it will take some time to solve it, but you know the method. You have to first put this equals to 0, t is equal to 0 to get x naught, then take the derivative of, find x dot of t, find x dot of t, whatever, which means the derivative of this solution, and that then put that equals to v naught, and then find two constants. So by solving this, and I hope you can solve this, okay, for the sake of simplicity, for the sake of the solution simplicity, you can put this factor, equals to p, because you cannot derivate this factor because it's a constant factor. So then your solution end up will be like this: x of t is equals to capital X e minus zeta omega nt sine of omega dt plus phi plus p sine of omega t minus theta. So this is what the total solution, where p, as you know, is this whole factor. Okay, the putting the two initial condition and solving it, we get x equals to, which is this, which is equals to small x naught minus P cos theta over sine phi, and phi is equals to tan inverse of omega d into x naught minus P cos theta divided by V naught minus zeta omega n P cos theta minus x naught minus P omega sin theta. If you solve the above equation, this equation, by using two initial conditions, what in x of 0 equals to x naught and x dot of 0 equals to v naught, by using the same method as we have done in the free vibrations, and try to find out what x and theta is, because there are only two unknowns, which is x and phi. And remember, the theta is same that we have derived in the modeling, that is tan inverse of 2 zeta omega by omega n divided by 1 minus omega square over omega n square whole square. This is what the theta is. And P, as you know, is nothing but f naught over k divided by square root of 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Clear? So this is what the solution. Before that, this is the x of t, and by using the initial conditions you have to find out, okay, if you only interested in the particular solution, then maybe you don't require any initial condition, because there is no unknown. I hope you understood this lecture. In this lecture we have talked about the modeling of how to model the forced vibration. We have seen which factors are important in determining the amplitude of the forced vibration, and we have seen the graphs, that how the amplitude varies and which factor we have to control. And finally we have seen the one application, that is the application of rotation and balance. And I told you in many real applications in which the center of mass does not align with the center of rotation, normally unbalance occurs, and that unbalance creates forced vibrations, and you can analyze these forced vibration, and to eliminate it we have to balance the body, otherwise the vibration will take place continuously. The last part of the slide, I just want to show you a video in which actually a resonance test occurs. Just in the case, you can imagine this physically. So what happens here is, this is omega. This is omega. This is a shaking table, and you're providing omega through this shaking table. Now every mass has a certain omega n. The omega n, omega n, and omega n. It can be different. It has different value. It has different value. It has different value. As you increasing omega, because this is the length is high, its stiffness is slightly smaller, so its natural frequency is slightly smaller. So it will first resonate, this mass will first resonate, and you can see by the vibrations, because these three masses are actually installed on the same table, and you can see this mass is actually vibrating. Look at this mass. So the other two masses are relatively still, but this mass is vibrating because the omega becomes equal to its natural frequency, which is 4 Hertz. Yeah. Now we keep increasing omega. If you keep omega, what happens? That this try to remain still. Now it has gone to post resonance. It's across the resonance. Clear? Now, because its frequency is slightly higher than this, if the frequency of this mass is higher than this mass, so what happens now? This try to resonate. Clear? If you look at closely this mass. Clear? Now it is vibrating at 6.35 Hertz, which means natural frequency is 6.35 Hertz, and because when omega here becomes 6.35 Hertz, this resonate. And resonance means you see a very high amplitudes of vibration. As you can see in this diagram, in this video, you actually got a very high amplitude of vibration. If keep increasing omega, this mass then becomes still, and now which is the smallest length has the highest stiffness and has the highest natural frequency. Now this tends to resonate. Clear? Now you can see now closely that this mass is both these mass are relatively still. Clear? But your actual this mass is trying to vibrate, and it's actually, you can observe the resonance when you have got to a sufficient amplitude of vibration, which is definitely higher than the normal vibrations amplitudes, and that is see the amplitude of this mass, it is 11.35 Hertz. This is where this is a natural frequency. So what we have seen is the natural frequency of this mass is, okay, I think so you have actually understood this point, that this is what we are actually talking about. So last but not the least, we have talked about the modeling of damped forced vibrations. Okay. We have talked about the one application, which is rotation unbalance, that actually causes the forced vibration, and last we have seen the solution of forced vibrations. So these are the main contents of our topic today. Hopefully you will understood this this topic. Now in the coming week we are actually have to solve some problem, as I told you in the start of the lecture, from some exercise problem and some examples and some other problems. So it's my humble request to kindly go through this modeling. So we'll use some formulas. As I told you previously in the start of this course, I have not included these kind of modeling in the paper because this is just to give you an idea that how we model vibrations. But during the solution of the problems, we will use some you can say some formulas that we have derived in this lecture to actually see how in many real different types of problems these formulas have been used. Thank you very much for your patience and time. Hopefully you have understood. Meet you inshallah next time.